We hear the words algorithm and model thrown around constantly today, usually as if they mean the exact same thing. In reality, these two concepts sit at opposite ends of the development process. Conflating them hides how modern AI actually functions. An algorithm is simply a static mathematical procedure. It is a rigid, step-by-step set of instructions written by a human to solve a specific problem. Early artificial intelligence, known as symbolic AI, relied entirely on these rigid instructions. Developers tried to explicitly code rules for every possible scenario, but the real world is simply too unpredictable to hardcode. To achieve true machine learning, developers stopped trying to process tasks with static rules. Instead, they used algorithms to ingest massive amounts of raw data and forge an entirely new entity, the model. The model is the autonomous brain produced by the synthesis. This shifted computing away from following rigid instructions toward a system of dynamic, data-driven learning. Think of a neural network as a structure built to mimic the human brain. It learns by passing massive data sets through layers of interconnected nodes. Inside this network, every connection has a parameter called a weight. A weight determines the exact strength and influence of an incoming piece of data. Each node also contains a parameter called a bias. A bias acts like an offset dial, shifting the activation threshold so the network can fit messy, real-world data. When making a decision, an input is multiplied by a weight, shifted by a bias, and pushed through an activation function. This mathematical equation introduces nonlinearity, allowing the model to learn complex patterns instead of straight lines. An AI model does not store a database of facts. Its entire knowledge base is held within a collection of millions or even trillions of these perfectly calibrated weights and biases. When a model first begins training, its weights and biases are randomized. It makes a blind guess, calculates how far off that guess is from the actual data, and then has to figure out how to fix the mistake. It uses backpropagation, a critical algorithm that works backward through the network, fine-tuning those parameters to minimize the prediction error. This optimization scales up massively in advanced architectures like transformers. Transformers use a mathematical technique called attention to weigh the importance of different parts of a data sequence, identifying how elements influence one another. When you speak to a digital assistant, the model doesn't process individual words in isolation. It uses its optimized parameters to weigh the surrounding words, parsing the context to understand human speech. The training phase ends when the error rate is minimized. What remains is a frozen, highly optimized decision engine ready to be deployed into the real world. Once deployed, a trained model generally applies its parameters in one of two ways. It acts as either a discriminative model or a generative model. Discriminative models are boundary drawers. They classify data by predicting conditional probability, allowing them to determine if an object is a vehicle or a pedestrian. Generative models, on the other hand, are distribution mappers. They calculate joint probabilities to assemble entirely new, highly probable sequences of text, audio, or imagery from scratch. Whether a system is categorizing a photograph or writing a complex essay, its capabilities rely entirely on the exact mathematical parameters locked in during its training phase. Every weight and bias we've discussed is forged by a specific dataset. Because that data consists of human-written text and human-captured images, the resulting model acts as a permanent mirror of its creators. This creates a conflict between the necessary mathematical bias we use to fit data and the devastating reality of systemic human bias. When historical human prejudices and blind spots are present in the training data, those flaws become permanently encoded directly into the model's foundational weights. A biased human manager can be retrained or replaced. A biased AI model applies its prejudice automatically, instantaneously, and often undetectably across thousands of bulk decisions at once. Excising this systemic bias is nearly impossible. To remove it, engineers would have to unbake the millions of intertwined mathematical parameters that allow the model to function in the first place. This is an autonomous collection of flawed human data, mapped as probabilities, a powerful tool that demands intense scrutiny rather than blind trust.
AI isn't just another tool. It's an intelligence system for your dealership. Learn how at autoagentic.ai.
Or get your free copy of the Automotive Playbook for rebuilding organizations around AI. Also at autoagentic.ai